Hello, good morning, good day. This is a continuation of our EASY lecture series on modeling and simulation, realistic modeling and simulation of earthquakes, soils, structures, and their interaction. We're back after almost a month of break. As you can see, I'm actually back in my office in Davis, California. Took a while to get back to California from Europe. Joining me are again Dr. Han Yang.
Hello.
And Mr. Heshen Wang.
Hi.
They're both in Davis. We're all now in Davis. At some point, we need to get together in a room and start this again, but we have to follow Yolo County measures for coronavirus. Coronavirus is still on, and actually, in fact, it's increasing. The number of cases are increasing in California. They're going to reintroduce lockdown, but so be. So today, we're going to have this first lecture is going to be introduction, overview of some practice-oriented, fairly simple but fairly powerful models for modeling of nonlinear, inelastic, elastoplastic behavior of soil, sand, and clay. And this is the first lecture. So Heshen, please go ahead. Share your. I need to allow you to share screen, right?
Okay. Yeah.
Okay. Try now to share.
Okay, so
Good.
now you can
Excellent.
see my screen.
Yes.
Okay. Yeah. Okay. Okay, maybe this way. Okay. Yeah. Good morning, everyone. So today we're going to talk about the choice of elastoplastic models for soil and interface in Real Easy. Specifically, I will going to talk about the elastoplastic model for clay, elastoplastic model for sand, and also the elastoplastic model for interface, contact, and joint. And
Okay, I'm sorry, Heshen. Can you make it one slide at a time so we don't have to scroll? Can you just make it one slide at a time so it goes one page at a time?
Okay.
Just scrolling sometimes gets confusing.
Yeah.
Yes, perfect.
Okay.
Excellent.
Yeah.
Thank
yeah.
you.
Okay. Yep. We are here. So we will start to talk about the model for clay. As we know that clay usually has a very low permeability. So during a very short time earthquake shaking, the clay will have a negligible pore pressure dissipation. Therefore, usually it has a pressure independent shear strength. And in practice, the strength of the clay is usually characterized by an undrained shear strength. And we can model the elastoplastic behavior of the clay using a simple Formises elastoplastic model with the Armstrong-Frederick translational kinematic hardening. And so this is the model we're going to use. And we're going to use the Formises yield surface with the associated plastic flow. As you can see here, this is the yield function. We can see here the shear strength is pressure independent for the clay. And this is the formula for the yield function. We have a parameter, which is so-called Formises radius K, that will control the size of the elastic region. And we will also have a backstress here, whose evolution will be controlled by the Armstrong-Frederick kinematic hardening rule. And for this Armstrong-Frederick kinematic hardening, we have two parameters. Number one is the parameter HA, and which controls the post-yielding initial stiffness. And we also have a parameter CR, which when combined with the parameter HA, the ratio of the HA over CR will control the plateau of the backstress saturation.
Yes. Yeah. So if I may go back for a second, if I may add, so essentially doing this, you essentially control the shear strength, because then this plateau plus the actual K, the square root of 2/3 of K, this is the radius of the yield surface, essentially controls the shear strength. And you'll show some examples later on. Okay, go ahead.
Yeah. And this is the real ED DSL that you can use to apply this model. As you can see here, we have 7 parameters for this model. We have a parameter for mass density, which can be calculated from the unit weight measurement of your soil. And we will also have a 2 elasticity parameter, which is the elastic modulus and the Poisson ratio. And these 2 parameters can be easily converted from the in situ measurement of your shear wave velocity or P wave velocity of your site. And also we have a parameter for Formises radius that I mentioned that before, that control the size of the elastic region. And also we have the 2 parameters, the Armstrong-Frederick HA and Armstrong-Frederick CR, that you need to calibrate to match the, to control the post-yielding hardening behavior, and also need to calibrate to match the undrained shear strength of your soil. And there's additional parameter, which is isotropic hardening rate. Here, for the modeling of the soil, we generally find that isotropic hardening is not that realistic and useful. So we will set it as 0 for no isotropic hardening. Well, okay. So then we talk about the go to talk about the elastoplastic model for sand, and we know that sand is very different from clay. Its shear strength is increased with the confining pressure, and in practice, the strength of the sand is characterized by two parameters, which is usually the cohesion and the friction angle, and the shear strength is governed by this linear equation. And to model the elastoplastic behavior of the sand, we can use the hyperbolic Drager-Prager yield function with non-associated plastic flow and combined together with the Armstrong-Frederick rotational kinematic hardening. So this is the, so we will first talk about the hyperbolic Drager-Prager yield function. So as you can see here, now the shear strength of the material is increased with the confining pressure. And we have three parameters to quantify such a yield function. Number one is the friction angle, which is the slope of the asymptotic line of this PQ line that will control the size of the elastic region for a given confining pressure. Yeah, yes, Professor.
Actually, I'm sorry for interrupting, but officially, theoretically, friction angle is actually not the slope of QP line. Friction angle is slope of tau sigma line. But there's a simple equation to convert friction angle to be a slope of QP line. So friction angle is really in that space tau sigma, and that's the friction angle. When you move to QP line, QP space, again, there's a one-on-one equation to convert that angle for this, okay?
That's true, yeah. And also we have a second parameter, which is the cohesion, that will control the intercept of this yield function along the Q axis. And also we have a third parameter because for this hyperbolic Drager-Prager model, we want to our model to take a little bit of tensile stress. So we also need to specify a third parameter called the rounded distance, which is the distance A in this figure, that will control the intercept of this yield function at the p-axis. Essentially, this is the uniaxial tensile stress of your soil, tensile strength of your soil.
And if I may add again, cohesion is really not well, it should really be intercept on tau axis. Remember that all of this actually, anytime you talk about frictional, it's all tau sigma because that's the way they've done it. They've done it a normal axial sigma and then shear tau, and then we can easily convert to QP. But okay.
That's why
a lot more about this in lecture notes. In fact, there are all these equations in lecture notes. So anyway, you'll mention at the very end link through realeasy.info. So and there's a link to lecture notes. Anyway.
That's why, so the cohesion here is control the intercept, but it's not exactly the intercept as the Q space. You need to, there is a linear mapping between this value and the real value you get at the PQ space. And also the second part, which is very important, is the non-associated plastic flow. We're going to have two parameters to quantify this non-associated plastic flow, which is C and KD. As you can see here, we have a yield function, and we also, for non-associated plastic flow, we will have a dilatancy surface, and the parameter C, which will govern the amplitude of the plastic volume change of this plastic flow direction, and also the another parameter KD will control the size of this dilating surface. So as you can imagine that if we set our plastic flow KD equal to 0, this dilating surface will shrink to a hydrostatic line, which is essentially the p-axis. And to complete the model, we also need the third part, which is the Armstrong-Frederick rotational kinematic hardening rule. And again, we have two parameters for that. Parameter HA is controls the post-yield initial stiffness, and the parameter CR, when combined with HA, the ratio of HA over CR will control the plateau of the backstress saturation. And because in our yield function of the Drager-Prager hyperbolic Drager-Prager, we're going to multiply this alpha ij together with the confining pressure P as the backstress. So in the normal stress space, you will see the yield function, the yield surface of the Drager-Prager cone will rotationally move along with the evolution of the backstress, as shown in this picture. And for practical use, because the soil or the sand is plastified at a very very low stress level, so we generally set a very small or vanishing elastic region which by setting a very small friction
Yeah.
angle in the model parameters, and we will capture the pressure dependent shear strength through the rotational kinematic hardening.
Can I ask a question? So there was some funny noise just 5 seconds ago.
Yeah, yeah,
No, but going back here. So what you said is to put actually very small friction angle. This is really what's done in all the Falias models. They essentially have a very tiny cone, looks like this, and it rotates. And the actual friction angle really is once you reach saturation. So it shouldn't really be called friction angle. I would rather call it opening of the cone. So very small cones that start to rotate as soon as you plastify and you rotate. And in his case, he's using bounding surface plasticity, which we have implemented also. But in this case, we just use a nonlinear kinematic hardening from Armstrong Frederick. Go ahead.
yeah.
Thank you.
That's true. Yeah, and also I think it is also physical because for soil it's plastified at a very low, yeah,
Yeah.
the stress level.
Yeah.
Yeah. And for this is the real easy DSL that you can use for this model. As you can see here, we have going to have 11 parameters for this model. Again, similarly for the mass density and the plasticity parameters, and we will have a small. We will have a friction angle parameter, as I mentioned before. We're going to set a small values to achieve a zero of vanishing elastic region, and we also have a cohesion parameter that you can that come from the characterization of your soil, and also a rounded distance parameter, which we usually set as a similar value to the cohesion, but it should be generally should be a little bit smaller than the cohesion. And also we need to calibrate this Armstrong-Frederick HA and CR parameter to quantify the hardening behavior, and we're going to calibrate this parameter to match the pressure-dependent strength of the
Yes.
soil. And also we're going to set 0 for the isotropic hardening rate. And also there is a because for the drug product material it's pressure dependent, you can also set up initial confining stress for this material. And also eventually you also need to calibrate this non-associated plastic flow parameters, plastic flow C and plastic flow KD. And yeah, with that we can move on to the elastoplastic model for the interface or contact or
Let's
joint.
stop. Well, okay, yeah, go ahead. Yeah, I'm sorry. Yeah, go ahead. I'm sorry. This is just
Mhm.
introduction. Then we're going to talk about calibration later. Yes. Okay. Interface,
Okay,
contacts, and joints. And just
okay,
if I may just add, I used to call them contacts, but people get the wrong idea. You know what they think about contact is what's contact in LS Dyna. LS Dyna does not have these constitutive contacts. LS Dyna has contacts where things fly and then they get in touch, and they have a very good algorithms for this. We don't really worry much about that. In our case, our contacts are already in place. We have a foundation that's in contact it's an interface between concrete or steel and soil or rock. And then it's in our case, the interface contact joint models are constitutive. They're not geometric nonlinear, because the only thing that can happen is it can slip, it can open a gap. If it opens a gap, you lose stiffness. If gap is closed, there's a stiffness going on, and you're going to talk about that. So this
yeah,
is really for foundations on soils, for interfaces between different parts of concrete structures, or for example, for dams where you have blocks of concrete interface between those blocks of concrete. So please go ahead.
yeah. Yeah. As the professor mentioned that, yeah, our contact is really constitutive models,
Yes.
and we have two aspects for these constitutive models. And number one is the normal and axial direction of the contact behavior. So for the normal and axial direction, we will allow the contact to open and close, and we will enforce the no penetration of the contact node through the penalty stiffness method. So we're going to have two types of behavior for penalty stiffness. Number one is the called so-called hard contact, and number two is so-called soft contact. As you can see here, is the penalty stiffness for the hard contact. So when the gap is open, we do not have any stiffness, and when the gap is closed, we will have a constant penalty stiffness. And this type of hard contact behavior can be used for modeling of the concrete to concrete or concrete to steel interface. And on the other hand, we have another type of contact, which is so-called soft contact. So again, the same. If your contact is open, we do not have any stiffness here. But when the contact is closed, and we will have exponentially increase for the penalty stiffness of the contact, and eventually we're going to have a cap with the maximum axial penalty stiffness. And this type of soft contact behavior can be used for modeling of concrete to steel, or concrete to soil, or steel to soil interface. And other than to the normal direction of the behavior, we also need to have a shared direction behavior. The shared direction is we have three different types of nonlinear inelastic behavior. As you can see here, we can have either a elastic perfect plastic shear behavior as shown in the black line, or the blue line, the nonlinear hardening shear behavior, and also the red line, which is the nonlinear hardening softening behavior. And from our experience for common concrete to soil or steel to soil interface modeling in earthquake soil structure interaction, we find the soft contact with nonlinear hardening shear behavior works really well. And in Real Easy, this is a DSL in Real Easy that you can use for this stress-based soft contact with nonlinear hardening shear behavior. And for this model, we're going to have 9 parameters. And the first 3 parameters will control the normal direction of the penalty stiffness, its behavior. And also we have a parameter which is so-called initial shear stiffness, which is the initial tangential stiffness of the shear behavior of the shear direction. And also we have 2 parameters for the damping in both normal and shear direction. And also we have a very important parameter is the so-called the residual friction coefficient, which is essentially the tangent of your friction angle of your interface, of contact interface. And there's another parameter so-called shear zone thickness, which specifies the thickness of the contact shear zone. And one of the last parameter is also very important. It can be either the contact plane vector, which user can explicitly specify the normal of the contact plane. And also we have another type of implementation.
Hello? I just lost internet. I just lost internet. Yeah.
Can you hear me?
Yeah, I can hear you, but I lost Heshen's internet. Heshen, can you hear us?
Right. Yes.
I can hear.
Okay. I'm sorry. So go back.
Okay.
So you were talking about
Okay.
the first case, contact plane vector.
Oh, okay.
So this is to specify the normal to the plane of contact or interface, and then you jump to
Yeah.
the second one.
Yeah. We also have this second one, a second implementation, which is called automatic contact detection. So if you have a pure, like a bunch of solid contact together, we have an algorithm to automatically detect the plane of the normal of the contact plane. And in that case, you're going to need to specify the surface vector relative tolerance. And depends on this tolerance, we can identify multiple contact plane at a single joint, and then we will generate multiple contacts for that geometry.
So if I may add, so in this case, you either specify your normal. This is the first case, and this is useful, but it can be tedious for a large number of contacts. In the second case, if you have a number of solids, there will be a automatic calculation of normal from one solid, from one node, and there will be automatic calculation of normal from the other one. And this is where this tolerance comes into play. They're never going to be exactly the same because it's numerics. So you provide some small number. We'll give examples. You provide some small numbers, so normal from one and normal from the second one are, if they're close enough, they're going to be merged into one normal, and it's going to create normal automatically. So
Yeah,
we'll show
that's true.
examples.
Yeah.
Okay.
Yeah,
Right,
and with
please.
that, you can look more information on this reference, and also I would to give acknowledgement to our collaborators and the funding resources, and also the for more information you can check out our Real Easy website. Yeah,
Thank you very much.
thank you for your attention.
So in fact, funding sources, but more importantly, collaboration, because they do ask questions, they make requests, and they tell us what is important, and so this is really appreciated. And then if you go to this realeasy.info, realeasy.us website, you can find links to all the documentation and lecture notes and so on. Thank you very much. So I'll stop recording right now.